Hi everyone, and welcome to OPTEE Basics and Porting Review session. This is basically a beginner session, so covering some basic security concepts and also a quick review of some past Connect sessions, especially for those of you who had missed them or just like a refresher. Okay, so since this is more for beginners, our objectives here today is just to get a high-level overview and understanding of the topics listed here. We'll be covering security building blocks and the basics of Secure Boot. We'll also be briefly reviewing trusted applications and OPTEE porting as well. And this presentation actually leans more towards ARM v8, but we'll point out ARM v7 differences as we go along. So what is OPTEE? OPTEE stands for Open Source Portable Trusted Execution Environment, and it's actually Linaro's open source reference implementation of a trusted execution environment. And for those of you who don't know, a trusted execution environment, or a TE, is basically a computing environment provided by a secure operating system running on the same processor as a regular operating system. And in TrustZone, in ARM TrustZone nomenclature, we call this the secure world and the normal world. And the normal world is also sometimes referred to as the rich execution environment, or the REE. Okay, and OPTEE is actually sponsored by one of our members, ST Microelectronics. I'm not sure if sponsor is the right word here, but it started as an internal project for them, but they decided to open source it for everybody's benefit, so we're grateful for that. And some of the advantages of OPTEE, other than it being an open source, is that it's global platform compatible. And again, for those of you who are not familiar with global platform, it's roughly a cross-industry association which publishes APIs that promote interoperability for applications on security chip technology. And only the APIs are defined, but the implementations of the API themselves is up to the developers. And another advantage, obviously, is that OPTEE is compatible with ARM trusted firmware, and Linaro works closely with ARM to make sure that all the software components are in good order. And we also actually work with a Huawei assignee and a ST engineer who are actually members of the Global Platform T working group, so that we can ensure that our development progresses in the proper direction. Hopefully all that translates to less errors and less code for you to write. And finally, a complete system, meaning that many software vendors require or depend on a complete TE system to tag their solution onto it. So with ARM trusted firmware and OPTEE, they have such a system, and they can just concentrate on the differentiation of their products or solutions on top of the system. Any questions before we move on? Okay. Okay, so security building blocks. So what are the components that make up an ARM trusted system? So we're gonna learn what the components are. And on any system, you usually have the hardware, the firmware, the operating system, and the end user programs or client applications. So the components that make up an ARM trusted system begins with a TrustZone enabled SoC as the hardware. And on top of that, you have the firmware, which is the ARM trusted firmware, which offers both secure boot services and runtime services, like a monitor or a dispatcher for world switching and bridging. And for the OS, we have the secure OS, which is our OPTEE. The OPTEE is actually divided into three separate components. You have the normal world client library, a kernel driver, and the secure operating systems. And finally, on top of everything, we have the client apps on both the secure and the normal side to provide secure services for end users. Okay, so here you can see the components being laid out in a diagram in relationship to one another. The ARM trusted firmware components are actually in the orange and the red here, the tree here, and then the the OPTEE components are in the red and blue in the dotted lines. So you see the client library here, the driver, and this actually makes up the trusted OS, and we have trusted applications as well. And for you can see that for ARM v8, there are 4 exception levels that are defined. You have EL0, 1, and 2, and then EL3, and then the corresponding secure site for EL0 and EL1. So here we see a similar diagram, but this one actually shows more of the call flow and the interaction between the OPTEE components and ARM trusted firmware. And you can see the client calling into the driver via iocto calls, and the driver communicating with the trusted OS using the OPTEE dispatcher or the monitor. And this is being done using the ARM SMC calling convention. And as mentioned earlier, both the client and the internal API here, they are both global platform compliant, and you can get the specifications for global platform APIs from the global platform website. Okay, so with that, we've just gone through the components of the OPTEE that make up a complete system and solutions for vendors. Any questions before we move on? Okay. Okay, right, moving on, we're going to learn about Secure Boot, what it is and why it's needed. Secure Boot is basically just a generic term to mean a way to prevent unauthorized executables or images from running on a device. And obviously we need that because if a malicious user can trick you into running his or her program on your device, bad things can happen. So how does Secure Boot prevent that? So Secure Boot works by verifying the signature of an image before loading it. Well, not really running it, but loading it. So this sets the prerequisite that an image has to be signed before distribution. And just a really crude analogy is like when you go to a bank to cash a check, the bank will verify your signature before processing the check. So, and of course that doesn't really necessarily happen in real life, and that's why I say it's a crude example, but along similar lines, not all devices right now perform Secure Boot, but I think we're getting there. So for Secure Boot, the boot process is actually divided into several stages. And we have to start stage 1 with something that we already and implicitly trust, and we call that the root of trust. And this would maybe be analogous to the bank or the institution that you trust. And on the SoC, this is usually the round boot code. So the round boot code will verify the signature of the next image to be loaded, at stage 2. And we continue on where every subsequent image to be loaded is verified first by the one before it, meaning, stage 2 will verify stage 3, stage 3 verifies stage 4, and so on and so forth. So here we'll see a typical boot sequence for the ARM trusted firmware. So you can see here the round boot code, also called BL1, which starts the boot by verifying and booting the trusted boot firmware called BL2. And then for ARM trusted firmware, BL2 actually verifies and loads 3 different components at the 3rd stage. So namely the secure monitor here, the trusted OS, and the normal world bootloader, UFi or U-boot, which will eventually load your kernel. So why go through the pain of so many stages or levels? But we want to make sure that all these components, the ARM trusted firmware, OPTEE, the bootloaders, and the kernel, all of them are verified, because otherwise all the cases that the use cases that security is meant to support doesn't really make sense anymore. Okay, so we've just quickly gone through Secure Boot and how it works and how it protects the integrity of a system. Any questions? Okay. So now we're going to look into trusted applications, what it's used for, and briefly go through how to create one. So when you have all the previously mentioned building blocks and components in place on this, in your system, the next thing you want to do is you want to write trusted applications to offer services to end users. And usually there are two parts to trusted applications, one for the normal world and one for the secure world. And in most cases, if not all cases, they are a corresponding pair, much like what a client-server system would do. So here you see the basic components in place. The OPTEE client here, the driver, and the trusted OS. And as mentioned earlier, you can see the trusted applications being built on top of them to provide some services, like a few sample services you can see here, like DRM services, payment services, and corporate services. So, and usually the common use case is that a client would receive some sort of encrypted data, pass it along to corresponding trusted applications on the secure side to be decrypted for access. Okay.
Can you go back one slide?
Yeah.
So, like like for example, the DRM trusted application, how does it get? Who signs that?
The OS will sign the trusted application.
So, what is it that the DRM trusted application cannot do that, like a that the secure OS can do? Like for example, if there's a eFuse or something like that on the secure world, right? Can a trusted application, like a DRM trusted application, can it look at the eFuse, or
look at what? Sorry, look at what?
Like eFuse or keys or something like that, right?
User keys.
Yeah, not the user keys. I'm talking about like Silicon has some fuse keys, right?
Yeah, you shouldn't be able to access the keys that like hardware unique keys and such. That should be hidden. Only the secure OS should be able to access it, if it should be. I mean, in some cases you cannot even access the hardware unique key. You derive a new key based on that key. So if someone can access it, it's the kernel in the secure side. Otherwise, not.
So, excuse me. I guess the secure OS provides the root of trust, and then you just work off of that to have your own chain of trust.
Secure OS can be SMB. Will it run on multiple CPUs?
We're working on that right now, I believe. So it's not there yet. Yeah, it's in progress.
If only the phone vendor can design the trust application, so there's a there's a lot of the trust requirement from application side. If every application needs a trust vendor design, is it a big job? The device vendor need spend a lot of efforts to sign.
So the signing facilities are there in the OS, but we leave it as a platform-specific implementation for, you want to control I suppose you want to control your own keys and stuff. So the signing facilities are there, but you just have to, how you use it is up to you.
It should be like certificate authorities, where you need to sign your certificate first from upstream authority, from some other.
Because there's a lot of different device vendors. For one application, I need to sign with different application vendors or third party.
What I mean is with certificate authorities, if you want to sign in your corporation your servers, for example, you first need your corporate certificate to be signed by some upper layer authority to propagate trust chain.
Maybe we
Same should be applicable there. Second level bootloader should be signed by those who made boot ROM, because only there you will have somehow encoded private part of certificate. Otherwise, it wouldn't work.
Maybe we need some guy like app store to do the certification job, and application guys pass their application to the to app store, and the app store contacted with different cell phone vendors to sign the application. It's possible, something like that. Or else every application guys need to contact the device vendors for the trust application sign.
Basically, how is the chain of trust maintained across the different?
It's hard to maintain.
I mean,
Yeah, it's working.
okay. The chain of trust you will have to have from the boot, of course. So when you can trust the kernel on secure side, then you can have keys that you have been used for signing the trusted applications. So when you're building the trusted application, you just use the private keys, and when verifying them on the secure side, you use these public keys you have. That's it.
The key ring is managed in the kernel, non-secure world, or maintained in the secure world, the key ring.
The key should be handled in the secure world.
Or but it will store from the secure world or directly store in the secure world.
Well, it depends. So if you currently we don't have any possibility to store anything in secure world in this solution, so we are relying on Flash today. That means you need to encrypt your keys.
Yeah, you can encrypt the key and then return to the non-secure and store from the non-secure file system.
Yes.
So now this also supported in this case file.
Well, currently, if you look into the source code today, this function that is supposed to do the verification is stopped. And the main reason for that is on v7 we believe that most of the companies, they have their own solutions already. They have their own tools to sign trusted applications, and yeah, and they have their own kind of header format how it should be done. So we decided that we remove it. But I mentioned, I think, on the lightning talk also that this has been a little bit confusing for people because we are saying we have a secure environment with trusted application, but we don't verify them. So we have said that we should add some kind of simple reference design how this should be done, and that will be done by us, I guess, in a few months.
So moving on. So with OPTEE, we use standard global platform client APIs, partially shown here, to create our trusted applications. So if you want to write a trusted applications, it will be very helpful to download and read the global platform specifications, and you don't need to be a member to get them. And a typical program flow for a trusted application on the normal world side would consist of the following calls. So you initialize context to connect to the OPTEE driver, an open session to load the trusted application on the secure side. Invoke commands allows you to control the operations and actions of the app on the secure side, and the close sessions and finalize context before you exit the program. So here we see a sample output for the Hello World program, and we see the 5 APIs mentioned previously and 2 commands being invoked, namely the increase value and the print hello world. And all these commands are user defined, so you can create as many commands as you need or want. So one thing to note that the client APIs are not very flexible and somewhat limited in functionality, in terms that they work somewhat like a user mode program for a device driver, where where you can only use like open, ioctl, or close. So for trusted application developers, there are many commonly used high-level APIs. For example, AES encrypt, AES decrypt, just to name a few. And that these high-level APIs that trusted application developers want to use and want them to be readily available for use without having to write a secure site counterpart for them. So with that in mind, the global platform is planning to introduce a new set of such APIs on top of the existing client APIs, and this will be known as the functional APIs. If I go back and I'll show you here. See these wrapper APIs here, they are optional. This will be the new to be released functional APIs. So, and note that this approach usually works like if for applications that are relatively not too complicated or it doesn't require any special handling on the secure side. So instead of just using these, you know, I can now just call higher level functions. Like I can generate a random number or something like that. Or call secure store APIs directly. So basically, you're implementing this and wrapping them up and provide higher level functions for your developers. So, and you can get more details for building trusted applications at this URL here. There's a session we did on a previous Connect, and also the source code for the demo for that applications here. And then global platform specs can be downloaded here. So we've looked at how we can create trusted applications and how you can use it to provide different kinds of services or allow your customers to provide them. Any questions before we move on?
So we talked about like secure in the client side or in the user space side. We're talking about user space applications talking to the secure side. Is there any infrastructure in place for a kernel driver to directly talk to the secure side?
Yes, no. We have a kernel API.
And is that also part of the global platform API or no?
Kind of. I mean, it's the same kind of functional that is exported inside the kernel. So you can call it directly kernel.
Okay, moving on. So this is a topic of interest for many SoC vendors, OPTEE porting. So before we start the port, there's actually a prerequisite for ARMv8 in that the ARM trusted firmware must have already been ported to your system. And the ARM trusted firmware porting guide can be found here. And for ARMv7, this is not a requirement, and you just usually have your own trusted firmware. And before you actually do a port, it will be also helpful to go through the references like the design doc for OPTEE, just to get a feel of what the different components are and how they interact with one another. And then it will also be useful if you ever need to debug any issues you have. And also, there are also other documents here, like the our explaining what the build system is like, you know, file structures and folder layout and such. So this is a diagram you should be familiar by now. You see the client library, the trusted OS, and the driver. So for porting, we actually only need to just port the secure OS component. So for the secure OS, we need to add a new platform support. Again, no changes required for the driver and the client. You can just build them using the instructions available on the OPTEE GitHub. The driver right now is being built as a module, and the client's built at the shared library. But we are in the process of trying to upstream the driver code into, you know, upstream kernel. Just so you don't have to build it separately. So assuming that the ARM trusted firmware has been ported, you can start porting OPTEE by getting the OPTEE source code and the cross compiler for it. So before, obviously, you want to try building it first, and you can build it by defining the following exports, macros before running make. So at the toolchain path, the cross prefix, target platform, and the target flavor. So a platform is a family of closely related hardware configurations, and a platform flavor is a variant of such configurations. So when used together, they define the target hardware on which OPTEE will be run. So for example, for Juno, the platform will be Versatile Express, and the flavor will be Juno. And you can actually combine the platform and flavor, by defining a platform underscore flavor flag by using a dash. For example, like VA Express dash Juno. And the result of the make, of the compilation is a TEE bin file. So this slide just shows a sample partition map for some of the build components, and it's actually based off the layout of the all-winner AAD board, one of the boards which OPTEE has been ported to. So it's not entirely accurate, but it's just using it as a sample here. And for ARMVA, the OPTEE is actually embedded inside the ARM trusted firmware FIP.bin image. Okay, so the most direct way to create a new platform is probably to just to search for an existing platform that's closest to yours, and you just clone the platform directory under core/arch. And most of the platform-specific changes will happen under this directory in the files listed here. We'll look at some of these files next. So in the config.mk file, we have our compiler options. This is where you'll list your cross prefix, your platform flavor, CPU arch, and other additional compile flags. The link.mk file contains rules to link the TE core and perform any related tasks. The platform config file here is where you define, you find most of the defines required for your platform. You can allocate stack sizes, start address and sizes for various RAM defines, and also number of cores. And the list is actually quite long to go through here, but in general it also covers like I/O devices like your JIT controllers and your UARTs. So any questions before we move on?
Why do you need to specify the number of cores?
I think we have the state that keeps tracks of context based on which core that is executing for the moment. So that's what we use for.
I guess so, the stack as well, but you want to know how many stack you need to allocate as well.
Yeah, I mean it's used for currently.
I was saying because you're running in one of the cores. The OPTEE runs in one of the cores.
Yeah, but we don't know which core. So it could be different.
Okay, so each directory that contains source files has a makefile called sub.mk. It defines the source files that should be included in the build, as well as any subdirectories that should be processed as well. So if you need to add additional source files, you can include them in the build by listing them in it as well. And here we see a sample layout of the memory map as defined by the core boot config file. We have allocations for the T itself, trusted applications, and also the public shared memory. So just one thing to note is that we're currently working on moving the public RAM from secure world to normal world, meaning from the top here to the bottom, so that we can simplify some of the memory allocations and configurations for secure boot. So if you look at the internals of the core boot config file, you can see that it allows you to edit the configurations of different memories mentioned previously. And you can also add more platform I/O devices here under type memory IOSEC.
Does OPTEE have like malloc functionality? are there any limitations to that, like in terms of contiguous memory or anything like that?
Well, I wouldn't say limitation, but there's a size limitation.
Size,
But there's none, so you just use it as we're used to.
Is there a limitation of trust application size in the security board?
Yes and no, I would say. It's what you can see here. It's I think it's 32 megabyte. That is the default configuration. You can of course change that if you want to, but depending on how you configure the TRAM and PubRAM, the rest will be left for the TA RAM, so to say.
So actually, then the problem again. So every vendor's configuration is different.
Yeah, sure.
So that makes the TA application developer is very tough.
Sure, but I mean you have some constraints, so that's.
Yeah, maybe we need to define a minimum requirement and maybe the maximum size, for example, 4K or 8K for easier the developers like.
Yeah, but I mean it's configurable. It's depending on your. In software, it's easy to configure, but it depends on how much memory you have in hardware and how you want to partition it.
Yeah, because the high-end guys maybe has big memory, low-end chip, but when the application developer cannot differentiate, put different applications on different devices, right?
Well, if they create that big trust application, then they're creating really big trust applications. So I would be a bit surprised if they couldn't fit into a normal configuration.
No.
Does OPTEE Secure Apps have access to the file system?
No, yeah. As I said before, it doesn't have any secure file system, but it have access to the normal flash. So there's a daemon running on in Linux, and you use RPC to communicate, so you can store or write and read and write and so on.
So to say it again, you suppose that there is no secure partition?
There's no secure.
I guess to answer your question, you would obviously when you port it to your hardware, you would define, you allocate space for it, and that would be your maximum that you define, and then you would tell your trusted app developers what the maximum is.
Yeah, but every platform is different. That's the problem.
For example, if I want to allocate some MMC in ARMTF, I can allocate some hardware to be only for secure vault, because on the bus actually there is a signal of security. And if I'd like to allocate, for example, one of MMC controllers to be secure vault only, logically, file system that I have behind this controller is also belong to secure vault. But you say you don't support secure partition. How it works together?
I mean, if you're talking about peripherals, you can, like you're saying, you can configure them so they are accessible from secure world, and you can even change between normal and secure world. But if we're talking about plainly storing data on some file system in Flash or something, then in the current configuration now we use this, as I mentioned, mechanism to store the files in Flash.
I understand. So it will just work without any...
Yeah, yes. So it will go through this shared memory that we have. So you put the files in the shared memory, and then it will go back to Linux, and it will store it during using normal POSIX call.
Okay, so next we'll look into several platform initialization functions that you don't necessarily have to change, but you'll want to know what's going on in case you ever need to debug. So number one here, when the system boots up, the entry function start here, specified in the linker script will be called, and here you config the the cache and set up the MMU. If you're on V7, you also init all the CPU cores and BSS sections. And we jump to main init, the main init function here, number 2. And you should take care of setting up the UARTs, canaries, and your jig inits. And then for V8, we'll clear the BSS sections. For V7, we'll register the monitor vector tables. And then here you also register thread handler that points to functions to be called when you enter secure world. Number 3 here. And the standard default handler registered is main TEE entry, which we'll see in the next slide. And then finally, you'll init the TEE core before returning. So here we see what happens on the world switch. So the number 4 here, the OPTEE driver initiates an SMC call by generating an SMC exception. The exception will be trapped in the monitor, which will do some bookkeeping here, like saving caller contacts, etc., and decide where to go next. And in our case here, we want to go to the secure world. And on number 5, when we get into the secure world, the first thing that happens is assigning the threads for the task. And then number 6 here, just normally this will point to the main TE entry function, which we registered earlier in the previous slide. And if there are no special handling required, this will just call the TE entry function, which will then later call into the TE core. A little bit detail here, but it'll make sense when you go through the source code, I suppose. So testing and verification. So to test the port, you would basically do what we did earlier for in the trusted application section. So you would create a trusted application pair, compile them, copy them to the root file system, and just make sure that they run. And if you use our build script on GitHub, I believe that the Hello World test program is automatically included. And if you're a member, you can also get access to a whole bunch of test suites that test, end-to-end functions from the normal world client applications all the way to the trusted applications in the secure world side. So I've shown you this earlier. So just the URLs for the creating trusted applications. So again, similar logs and test output to what we saw earlier in the trusted application section. But here you can see that the driver is actually being loaded. And we're actually also loading a helper library or a daemon required for trusted applications to run. And then finally, we run the applications. And in this example, we're just incrementing a counter in secure world. So as a summary, I listed all the steps required for basic steps for porting OPTEE into a checklist here. The main task will be you port ARM trusted firmware without OPTEE and make OPTEE platform-specific changes. You build OPTEE, rebuild ARM trusted firmware with OPTEE, and then build all the other required components like your kernel and your root file system, flash the images, and then you just test and verify. So we've gone through the details of porting OPTEE to a new platform, and as a summary today, we've also gone through the basic security building blocks, secure boot, and introduction to trusted applications. So if you need more information, please you can visit the URLs here. Questions?
How does this work when we have upgraded the main image, or we have upgraded the image, and now what happens to the trusted application? Do we need to reassign it, or it works with the same upgrade image?
Can you speak up, please?
I think the question was if we need to update the trust application also in case we update the core itself. And no, you don't have to. I mean, if you sign it with the same keys. The trust application is standalone files just laying in the file system in Flash.
But that trusted application can be from a different organization, for example.
Right, but you're calling.
But you're calling into a standard set of API defined by global platform, so it will always be compatible. Is it right?
Well, I understand what you mean, but I mean, if company A and B have given you a trust application, they will sign it, and you still have the same keys in the kernel in the trusted OS. So you don't have to update it. I mean, it will stay. You use the same set of keys, so to say. But you need, of course, to update the binaries on the file system. That's what you need to do.
What is the license for OPTEE?
BSD2 class.
BSD.
Yeah.
If I write a 32-bit application for Allwinner, which is compliant with global platform, does the same binary will work on Juno? Or I need to recompile my trusted application for Juno?
It should work. I mean, it's just compiled the same way, so it should work.
And does the same application will work with a different trusted OS as well? If my application is global platform compliant?
Actually, not necessarily. And the reason for that is that they haven't really stated how the binary interface should look like. So depending on how you choose to implement your signature verification scheme, you will get different outputs. So that is a thing that would be really good if people could get some kind of agreement. One step could be to use X509 certificates or something, then it's a step closer, but still you need to agree on the header used, and that hasn't been done yet.
So I guess this secure EL1, the secure application context memory map will be the same between Allwinner and Juno. I mean, in terms of memory, in terms of virtual memory map, it will be the same view, or should I expect to see some differences in the user application, in the secure user application space?
I think I have to come back to that question.
Do you have a concept of do you have a concept of driver for OPTEE, or like if I want to do a Bluetooth driver, does it make sense for OPTEE? Or?
Maybe, but in general we try to not put too much functionality in a secure side environment. It is possible, but we try to avoid it. I mean, just for security reasons. So, but one example that will probably show up quite soon is if and when we start work with trusted UI, you need to have some kind of access to the device, display, and some I/O.
So should I understand this interface is it's hard coded. It's more like it's not. I cannot add new interface to my OPTEE trusted OS. You need to change OPTEE interface to cope with new interface. Yes,
right now, if we should add support for devices, it's hard coded. We have one of our members have asked if we could add some kind of driver SDK or something for the secure side also. So that is something we consider doing. Haven't done it, but it might happen in 2015.
So does the concept of driver, trusted driver, as part of the global platform, or?
No, it's not. Just now, since we talked about global platform and so on, global platform is defining APIs. If you compare to this U with normal world on the left side and secure side, they are defining APIs for the clients in Linux, and they are defining APIs for the clients on secure side. But what happened in between, there's a gap, I would say. And we have tried to propose some ideas how you could some more kind of generic interface. And but that is the tricky part when it comes to communication with our vendors doing the same kind of job.
So there's some discussion about using, I mean, if we want to do UFi Secure Boot or these kind of things, to use a trusted OS to do that. So where my non-volatile driver storage will be, is it part of the non-secure world, or it will be part of the trusted OS?
I think UFI have requirements that you should have it in secure NOR flash or something. So that was one of the problems we saw when we looked into it. So first you have the problem, how should you have both the UFI firmware, you have a Linux kernel, and you have a secure side, and these are three environments which would like to be in control, all of them. So you need to sort out the communication between them, and then also, as you said, devices might not have the possibility to store in a secure side. So then it fails more or less, because you can't really trust to put UFI authenticated variables in normal world flash, because you don't have replay protection and it's not persistent storage. So in that case, it would require you to have some secure side storage.
Do you have plans to support other OSs other than the Linux driver?
Depends on the main OS is. I mean, you can run it on Android if you consider that as an OS. So
I was thinking of things like Windows, for instance.
no,
There's no plans for that?
no, not from us.
Any more questions? Okay, we'll break for lunch, I suppose. Thank you, everybody.